So welcome everybody, and it's a pleasure and an honor to introduce our speaker today. Sorry, my daughters are working in the background. So our speaker today is Klaus Ritzberger, who everybody knows him, but I have to say some words about him. So everybody knows him from Vienna first, because he worked there and lived there for decades. Currently, he's at the Royal Holloway University in London, and he's specialized on game theory, microeconomics, and finance. He published his results in top journals like Econometrica, for example, Review of Economic Studies, Games and Behavior. And he serves as a referee for top journals too. And today he will present the result.
Now I've lost connection.
Yes, it seems that Klaus is not with us for a few seconds. So, okay, so until Klaus joins us, let's go on to the main dish. Klaus, please.
Okay, thanks a lot. So thanks very much for giving me the opportunity to present some of my work here. This is joint work with Jürgen Webel and Peter Wickman. With Jürgen I've co-authored before. Peter Wickman is one of Jürgen's brilliant students who just graduated a year ago or so. And this strange title, Solid Outcomes in Finite Games, is really about a topic that is most familiar to you. However, we take a somewhat different approach this time around. And the approach is motivated by the question of why game theory is actually useful for things like economics or other social sciences. And when you think about this, there's two answers that come to mind. One is, the purely pedagogical value of game theory, that it sharpens your mind and makes you understand strategic interaction a bit better. The other one is applications. Now, of course, game theory, game theory is actually not a theory, it's more like a language, right? So it's being applied not only in economics, but also in political science and other fields. But when we apply game theory in economics, then we very often try to explain something that we see in the real world, right? Or in the data or something like that. Some persistent phenomenon or some stylized facts that are hard to explain with the usual competitive model of economics, because these phenomena often involve some aspect of strategic interaction. So indeed, I've not only worked on the pure theory of games, I've also worked on applications a lot. And when you think about applications, then you realize that what you're trying to explain is typically a phenomenon that realizes under a variety of different circumstances. So it is a phenomenon that must be robust to the details of what happens, right? Because otherwise we wouldn't see it so often in the real world. So a phenomenon that is well explained by game theory is something that must be robust, not only to the usual strategy perturbations, the Selten's trembles, right? But also against lots of other things, against the payoff specification that we write down as analysts, also against the representation of the game, right? Whether it's an extensive form game or a normal form game, and many other specifications. So in a sense, the value of game theory derives from being a very stylized representation of what we see in the world. So it's like a roadmap, right? Very stylized, but useful. So that's the first thought that comes to mind when you reason about applications of game theory. The other one is that in applications, what you really care about is observables. Things that are reflected in the data or reflected in whatever you observe by whatever means. In economics, we often don't have the laboratories of physics. We don't run Large Hadron Colliders, but we rely on statistical data, the ONS, which is the Office of National Statistics here in the UK. That's the data that we rely on, right? So it's not really the counterfactuals that are so important, but what is important is what we can see in the data or in observations. This is a bit at odds with the older literature, because in the older literature, often players made speeches to each other in counterfactual circumstances that never materialize in equilibrium. Now, these speeches can never be really observed, right? Because they are off equilibrium. So they can also not be tested, right? And they cannot be refuted. So when you take this approach that you want robust outcomes, observable outcomes that are invariant with respect to details of the model, then of course, that will ring a bell to many of you, at least the older ones. Sounds a bit familiar, right? It does. Of course, what comes to mind immediately is the refinements of Nash equilibrium debate in the 1980s and 90s, and of course, strategic stability later on. True, that's also what we considered first, but all these things have drawbacks. So if you look, for instance, at extensive form refinements, like subgame perfection, sequential equilibrium, and whatever, then all these extensive form refinements are actually sensitive to inessential transformations of the extensive form, the Thompson transformations, right? So Thompson transformations are like, in a simultaneous move game between two players, turn around the order in which the players move, right? Make player 2 move first and then player 1. That's one of them, interchanging simultaneous moves. Another one of those transformations is that a player decides between 3 outcomes, and the player can either do that simultaneously, or we split it into 2 decisions, one where he either takes outcome A or not, and if not, he decides between outcome B and C. That's coalescing of information sets. So these are really transformations that shouldn't matter, at least if you adhere to a rationality paradigm. So these extensive form refinements are not completely satisfactory. The other approach, by imposing strategy trembles that dates back to Selton's ideas, like perfect and proper equilibrium, they have another disadvantage, namely they are fragile to adding or deleting dominated strategies, which is also not very nice, right? Then, of course, these are not new things, and people thought about this 30 years ago or more, which led, of course, to the strategic stability debate. Now, indeed, strategically stable sets, at least in the ultimate formulation by Mertens in the late 80s and early 90s, they do satisfy lots of invariances. But if you think of it, if you look at a very simple example, say a 2x2 game with 2 strict Nash equilibria, then there are actually 3 strategically stable sets. All of them are singletons. 2 of them are the 2 strict equilibria. But the mixed equilibrium, which must be there, is also a strategically stable set. that strikes us as a bit odd. Because, on the continent, everybody drives on the right side of the road. Here on the British Isles, they drive on the left side of the road. But I don't know of many countries where they randomize whether to drive on the left or the right side of the road. Maybe with the exception of India. So there's still something to be done in a sense. But what we want to do is really emphasize.
Klaus, excuse me, I have a quick comment on the slide before. The fact that applications do not care about counterfactuals, probably you don't need this for your argument, because otherwise a lot of macro and applied micro empirical papers would not be there, because they all care about what would happen if you take different taxes or different things. So I just didn't want to leave this. It's a little bit of I don't think you want to pick fights about that.
Oh no, but that's a different argument, Carl.
No, but you're saying, yeah.
But let me answer that, because that's important to understand. So what, for instance, a macro paper does that counterfactual policy experiments is it computes the equilibrium path if some exogenous parameter were changed, right? So this is something that we would observe would the world have been different, okay? So it is about the equilibrium path, not about off-equilibrium behavior, right? And refinements, or at least some of the refinements, not all of them, but some of the refinements were based on very elaborate stories of about what happens off equilibrium, happens in pure counterfactual circumstances, which, even though I've written papers like that myself, so I shouldn't be too harsh on that, but it strikes me as something that is at odds with the idea of observability, right? That's really the argument, okay? Does that answer your question?
No, I think that clarifies. We'll see how your model looks, but that clarified it to something. Thank you.
Okay. All right. So in order to combine the ideas of observability and robustness, we actually depart from the traditional approach to think of a solution as strategy profiles, right? So a Nash equilibrium is formulated as a strategy profile. That's the solution concept. Later solution concepts like strategically stable sets are sets of strategy profiles. Our solution concept will not be formulated in terms of strategy profiles, but in terms of outcomes. Whereby an outcome, what I mean is a probability distribution on the plays of an extensive form. Okay, plays are complete paths from the root to the terminal node in an extensive form, and an outcome is a probability distribution on these plays. Okay, so that's going to be our object, which means that we may not be able to exactly say how this particular outcome is supported off equilibrium. Of course, we know that it is supported in some way or the other, but there could be multiple ways in which this is supported off equilibrium. Okay? What we really care about is what happens in the end, right? Which terminal node do we reach with positive probability? Okay? So this is the solution concept that we propose. It's called solid outcomes. And it's based on combining two things: robustness properties that come from index theory and a set valued concept, which we call game blocks. I'll define this in a moment and you'll see what it is. But that's really the idea, to use, on the one hand, a strong robustness criterion, non-zero index, together with a set valued concept that gets rid of the mixed equilibrium in 2x2 games with two strict equilibria. Okay, that's the idea, and it's actually a very simple idea in the end. Now, for this concept, we prove a number of invariance properties and robustness properties, basically everything that has been proposed. And then finally, we also studied the relation of this concept to Meyer's sustainability notion. I think sustainability has been on the table in this seminar already about a year or more ago, when Rida Laraki presented his paper with Hari Govindan and Lucas Pahl on sustainable equilibrium. So the idea of sustainability is essentially that, let me formulate it first for equilibrium. So an equilibrium is sustainable if by adding extra strategies to the game, I can make it unique. So that's the basic idea. Now, we're not going to use exactly this idea because we want to work with a block or a set valued concept. I'll explain a little later which version of sustainability we use, but the intuition is very much the same. Now, what is the domain of our solution concept? That I should say up front. So the domain of our solution concept is a generic class of finite extensive form games with perfect recall. Okay. All right. Any questions at this point? Because otherwise I'm going to dive into the notation and the meat of the talk.
Yes, I've got a question.
Yes, go ahead.
So you say that basically instead of looking at strategy profiles, you consider the outcomes.
Yes.
But can't you reverse engineer given that you define a solid outcome?
Mm-hmm.
Can you reverse engineer the strategy profiles? Because of course now some outcomes off the path, you don't know what the strategy would have been there. But if you now change the game, then you can eventually find what the strategy would have been. So basically, I am asking, isn't there still a one-to-one correspondence between the outcomes
And the strategy profiles?
Yes.
No, it's not one-to-one. You're right that to a certain extent, you can reverse engineer what happens off equilibrium, but it's not one-to-one. You may end up with multiple strategies that support a given outcome. Okay? And that's actually, if you think of it, when you look at when you work on an application that is formulated in extensive form, that's actually what you do, right? You show that the equilibrium path that you derive in your application is supported off equilibrium by certain behaviors.
Yeah.
But these need not be unique. There could be many that support that, right? So the player off equilibrium plays a certain option with sufficiently high probability, right? That's good enough.
Mm.
So
Yeah.
we end up with an interval, right? The probability has to be sufficiently high, that has a lower bound and an upper bound, but this whole interval is possible to support the equilibrium. That's good enough. And I don't see why we should pick one particular point of equilibrium from this interval. As long as I can show that there is an interval that supports the equilibrium, I'm fine. And I actually, in the applications that I wrote, I never did more. I showed that it can be supported by something like sufficiently high probability, but not what exactly this probability is.
Yeah, I agree. I think I understand, and I agree with you to the extent I understand what you say. I think you're right, that indeed there is no need to exactly specify the concrete probability as long as it's sufficiently high so that the off the equilibrium path is good enough. But I'm thinking maybe you can still engineer a game such that your solution will have to kind of a game where the solid outcomes will be forced to define this probability exactly, but probably does not.
Well, that yes. So of course, in some games that's true.
Yeah.
We'll see an example of that later. So, or let me say this right again. Think of a perfect information game. Okay, a generic perfect information game, but then no ties. Okay. Then, of course, as you will see, the solid outcome is unique, and you can actually reverse engineer everything. Okay, and then it's one-to-one. But in general, that doesn't need to be the case. And actually, why would we want it to be the case? There's no point, right?
There can be different strategy, indeed, different strategies, traditional strategies supporting. Yes, you have convinced me. Thanks. I think you have convinced me.
I also have a quick question, Klaus.
Sure.
Will you, given your introduction, will you also have an application in economics that you will then show us that we get some new insights? Or is this more a preliminary step towards later on applications?
I'll not show you an application from economics. I'll show you an applications from political science.
Okay, that's good too. Thanks.
Okay.
I also have a question.
Sure. Bernhard.
Yeah, thank you. So, do you, to some extent, you could say the fact that we have a tree is a bit artificial, because sometimes you have the same outcome for different histories. Would you also allow, I mean, probably not yet, but I mean, have the same outcome coming up at different leaves of the game tree?
So I define an outcome to be a probability distribution on the place of the extensive form. So once you pick an outcome, or once you pick a degenerate outcome, a probability 1 on one of the place, you know exactly what the equilibrium path is.
Sure.
Okay. So the term outcome here does refer to a probability distribution on place, and not this. The word outcome has also been used for this intermediate map, right? So that
in game forms,
in game forms, yes, that you map from the place then into an outcome or a consequence, right, over which the players have utilities. I take this map to be the identity.
Okay. Yeah.
Okay.
Sure. I'm fine. Thank you.
Good. Okay. Then let's dive into the notation. So this should be pretty much standard. Normal form games are here denoted by G. S is the pure strategy space, so the space of pure strategy profiles, everything finite. U is the payoff function. When you see a tilde over the game, that usually means we refer to the mixed extension, where the strategy space is the product of the mixed strategy simplices. And with a slight abuse of notation, we'll denote the payoff function on that also by little u, even though it's extended by expected utility. Okay. Now, just to remind you of how we get to reductions of the normal form, payoff equivalents. So two strategies of the same player are called payoff equivalent if they give the same payoffs to all players for all strategy combinations among the opponents. This is the traditional notion of how you define the equivalence there, and that's a little bit stronger than what we actually need. What we actually need is Kuhn's original strategic stability notion that two strategies of the same player are strategically equivalent if they lead to the same outcome for all strategy combinations among the opponents. Okay, that would be good enough for what we do, but because of historical reasons, the payoff equivalence notion is used to go to the purely reduced normal form, or the pure strategy reduced normal form, which is essentially the normal form that you get when you collapse all the payoff equivalence classes for each player into single representatives. So you take the strategy space to be the quotient. Okay, that gives you what we call the purely reduced normal form. The best reply correspondences will always be denoted by beta. So beta I is player I's pure best reply correspondence. When the tilde decorates the beta, then it's the mixed best reply correspondences. And when I drop the subscript, what I mean is the product correspondences, either pure or mixed. And I guess in this audience, I don't need to explain what a Nash equilibrium is, right? Now, a somewhat less familiar notion is the notion of a pure strategy block. But it's a very simple object. So a block is simply a product set of pure strategy subsets, non-empty pure strategy subsets, one for each player. That's a block, okay? And of course, once I have a block, I can associate with a block the block game, in which all the players are restricted to play in their factors of the block, okay? And the payoff function is then restricted to the block. That gives me the block game. Now, blocks have actually been used as solution concepts for a very long time, right? I think the earliest thing is iteratively undominated strategies, which of course gives you a block in the end, right? And then rationalizable strategies. So blocks have been used as solution concepts, and there are finer concepts than iteratively undominated strategies or rationalizable strategies. Two examples of finer block concepts are curb sets. Curb is short for closed under rational behavior. So a block is curb if all the best replies to mixed strategy profiles supported in the block are in the block, okay? This concept has been introduced by Jürgen and Kaushik Basu in, I believe, the early 90s or something like that. So it's a pretty old concept. A more recent block concept is Peter Wickman's Nash block concept, which says that a block B is called a Nash block if for all equilibria of the block game, all the best replies are in the block. Okay, that's what Peter calls a Nash block. All right, then next let me remind you of one structure of the set of Nash equilibria of finite normal form games, namely that the set of Nash equilibria consists of finitely many closed and connected components. I think the first one to claim that was Kohlberg and Mertens in the mid-80s. But it's basically a relatively simple consequence of the fact that the Nash equilibrium correspondence is a semi-algebraic map. Okay, and this is going to be important for us, that these components. Now, as a definition, let's say that a block respects equilibrium components if every Nash equilibrium component is either a subset of the phase spanned by the block or disjoint from the phase spanned by the block. Okay, so it's either inside or outside. It doesn't go across. Okay, that's what respects equilibrium components means. And now with that, I can define our solution concept. So let me first start with the set valued part, which is a block called a game block. So a game block is a block that first respects equilibrium components, and second, it's such that the index sum across all the equilibrium components in the phase spanned by the block is +1. Okay, like it would be for the full game. Okay, so in a sense, a game block you can think of as a smaller game of its own, right? And indeed, in the end, we'll show that that is actually the case, right? That you can think of it that way. So this is just strategy blocks, the game blocks. Now, to come to the solid outcomes, let's denote by W the set of plays for a finite extensive form game, and by this M of W the set of outcomes that are induced by mixed strategy profiles. If I pick an equilibrium component, then M with the subscript for this equilibrium component denotes the outcomes that are induced by the equilibria in the component. Okay? And with this notation, here's the definition of a solid outcome. So a solid outcome is an outcome, so a probability distribution on place, such that this is the unique outcome that is induced by an equilibrium component with non-zero index and support in a minimal game block. Where by minimal, I mean set inclusion, minimal with respect to set inclusion. Okay? That's the concept. So to repeat, a solid outcome is a probability distribution on place that is the unique outcome induced by all equilibria in an equilibrium component with non-zero and support in a minimal game block. Okay? That's the definition, and that's the concept that we're going to study. Now, a first result, it's actually not really a result, it's just an observation, right? Solid outcomes exist for a generic class of finite extensive form games with perfect recall. That's a direct implication of the old result by Krebs and Wilson, that for finite extensive form games with perfect recall, there's only a finite number of equilibrium outcomes. Okay? So we have generic existence, and that's straightforward. That's not even worth a proposition. Now, to study the properties of this solution concept, traditionally one begins with looking at backwards induction, okay, whether this is consistent with backwards induction. Now, in order to check for backwards induction, I'll employ not sequential equilibrium, but employ a somewhat stronger criterion that was introduced by Eric van Damme in the early 80s, implies sequential equilibrium, but is much nicer, right? And that's called quasi-perfect equilibrium. Many of you will know that, but let me repeat what it is. So a quasi-perfect equilibrium is a behavior strategy profile such that every neighborhood of it contains a completely mixed behavior strategy profile against which the equilibrium is a best reply at all information sets. Okay? And, you know, stating this definition, you can probably sense why I like this concept, because I have been able to define it without mentioning beliefs at all. Okay? Now, of course, every quasi-perfect equilibrium is a sequential equilibrium, but not the other way around, because quasi-perfect has stronger implications. For instance, the continuation strategies at the given information set are undominated, which is not in general the case for sequential equilibrium. Okay? But the proposition that gives us backwards induction here simply says that every solid outcome is supported by a quasi-perfect and hence sequential equilibrium. So solid outcomes are consistent with backwards induction in this sense. Okay.
But for, if I may ask,
Yeah.
existence you only have in the generic, that's why you need genericity, I suspect, because for 3-player games you might not have quasi-perfect equilibrium in general, as far as I know.
This is general, so this actually is always true. The generic class we need because we defined solid outcomes as a singleton. Let me emphasize this again. So if you look at the definition of a solid outcome, we say that this probability distribution on place is the unique outcome induced by all equilibria in the component C that has non-zero index and support in a minimal game block. Okay. Now, of course, there's a trivial generalization of this definition. It says a set of solid outcomes is the set of outcomes induced by the equilibria in a non-zero index component with support in a minimal game block. Okay. But because of this, because we started with applications, right? We are saying we're insisting here on uniqueness. And that's where we need the genericity, okay? Because the Krebs and Wilson result that there's only finitely many Nash equilibrium outcomes holds on the generic class of finite extensive form games. That's where we need genericity.
Okay, yeah.
Okay. It's not needed for the proposition about backwards induction. Okay, so quasi-perfect, we have quasi-perfect implicitly, and that you could use to reverse engineer what happens off equilibrium if you want. Okay. There are, of course, other tests for backwards induction or consistency with backwards induction. For instance, one quite informative test is often to see what this concept does on perfect information games, right? Or generic perfect information games. Well, this is what the next proposition does. So we look at a generic finite extensive form game with perfect information. And then for this class of games, there's always a unique solid outcome. That unique solid outcome coincides with the outcome induced by the unique subgame perfect equilibrium. And the unique solid outcome is supported on a unique minimal game block. Okay. So that works very nicely. Everything becomes unique when you are in generic perfect information games. And it's consistent with the old idea of Kuhn's algorithm, subgame perfect equilibrium. Okay.
Klaus, your
Yes.
definition, your leading definition, involves indexes as in part of the definition. Now, application means that their applied people might be using this. Can you give an equivalent definition that doesn't involve indexes, or?
No. Why should I not use the index? The index is much easier to apply than any kind of Tremble or computing homology groups or stuff like that.
I don't think an
it's just
applied person would ever use a homology group. No, I was thinking more about applied people.
Certainly not. But
No, but you can
computing the determinant of a matrix, that's easy, right? That can even an applied person can do.
Also, you can give a characterization. I mean, the index one ones are the potentially unique ones, but that you extend the game and then it becomes a unique.
Yes. Yeah, I'll come to that a little later. That's the sustainability part. But you know, I don't see why you shouldn't apply the index, because it's just computing the determinant of a matrix, right? And you don't even have to do that nowadays. The computer does that for you, right? And it's much easier than looking for proper perturbations or looking for computing the homology groups in Martin's definition of strategically stable sets or things like that, right? The index is really easy to apply. Right? Carl, are you happy with that?
I'm very happy. I think this is something that one has to think about, but I see the point now. Thank you.
Yeah. Okay.
One question. So the proposition is basically a consequence of your previous proposition and your work with De Michelis and Zwinkers, right?
Indeed. Yes, absolutely. Okay. Yes.
Okay.
So a lot of these propositions are straightforward if you know the literature.
Thanks.
Okay. Actually, also the next proposition is pretty much straightforward. It's actually three different statements, but the proofs are identical for the three statements. So it's the same proof. So that's why we combined these invariance properties here in one statement. So this invariance here is about deleting a strategy for one player. Right? So suppose we look at the game and we have a game block B, and then for some player, we take a strategy that is not in his factor of the game block and delete it from the game. Okay, that gives us this game G prime. Okay. Now then B continues to be a game block for the game G prime if at least one of the following three conditions are met. Either the deleted strategy is weakly dominated, or its payoff equivalent to a mixture over other strategies, or it's not a best reply against any strategy profile with support in the block. Okay. Now, of course, these these three invariances have different meanings, but the proof is the same for all of them. What are their meanings? Well, the first one, that I can delete a weakly dominated strategy, implies that game blocks and solid outcomes are immune to the removal or addition of dominated strategies, okay? Which is not the case for things like perfect and proper, okay? The second one implies that game blocks and solid outcomes are invariant to the extensive form representation of the game. Because it means that a solid outcome and the game block, or a minimal game block, only depend on the purely reduced normal form of the game. And the Thompson theorem, or its somewhat improved version by Elmes and Rainey, basically is a characterization theorem that says two extensive forms differ from each other by these three, well, Thompson had four, but Elmes and Rainey had three transformations. So they differ from each other by these three transformations, if and only if the two games have the same purely reduced normal form. Okay? So the details of the extensive forms don't matter. That's what statement B says. And then finally, C is a traditional, the NWBR property, that game blocks and solid outcomes survive the removal of never weak best replies. Okay. Was there a question?
I have a question. I'm a little bit slow today. It looks like removal of dominant strategies that do not belong to the block is missing.
Yes.
Because you could also remove dominant strategies within the block and then it would change, right?
You could, yes.
And that's what I thought would have been this statement, right? Because we're interested in whether we can remove dominant strategies, but you say, no, we have to first check whether it's in the block, and then only can we remove it if it's outside the block.
Actually, we can remove it also if it's in the block, but then the block has to change because I removed the strategy.
Yes, of course. And that works then?
That also works, yes.
Okay, that's what I wanted to know. Okay, thank you.
Okay, so these are the first three invariants that I adopt somewhat strangely, independence of irrelevant alternatives. There's a further invariance, which is a little bit more difficult to introduce. So let me first explain the intuition and then formally define it. The intuition is the following. If you have an extensive form game, and you look at a particular terminal node, and then replace this terminal node by a subgame, which is such that the subgame has a unique and completely mixed equilibrium that gives exactly the same expected payoffs as the terminal node would have given. Right? If we do this transformation, then our solution should not be affected. Lacking a better name, I called this invariance the Meyerson-Weibull invariance because it pops up in the paper by Roger and Jürgen in Econometrica. So let me define what it is in the normal form. So you take a game and look at the particular strategy profile R, okay? And then you construct a new game by replacing the strategy little ri for each player I by a set of strategies in such a way that the payoffs in the new game are the same as in the old game, except when the players use the strategies in this block R, okay? And the payoffs when they use strategies in this block R are chosen such that the block game restricted to the block R has a unique and completely mixed equilibrium whose payoffs are exactly the payoffs that the strategy profile R would have generated. Okay? So this is this Meyerson-Weibull transformation. And then in order to formulate the invariance, we need to say what happens with the block, right? So if R is not in the block at all, then nothing happens. The block B hat is the same as the block B. If R for some player is in the block B, then we have to take away the singleton strategy little ri and add in the set of strategies capital Ri. Okay, that's how we get the corresponding block in the game G hat in the transformed game. And then the proposition says that if B is a game block in G, then this newly constructed game block B hat is a game block in G hat. And if B is minimal in G, then B hat is minimal in G hat. Okay, so we can do this intuitively replacing terminal nodes by subgames with a unique equilibrium. Okay, that doesn't affect the solution either.
Wait. You say a unique equilibrium, it's a unique, completely mixed equilibrium.
Yes, unique.
But that's something very different. Because something, so I was going to ask you, why are we interested at all in completely mixed equilibrium? I would have thought I would like to do this for a unique equilibrium, but you cannot do it for that?
That's a good question.
So I don't know why, I don't want completely mixed equilibrium anyway. So this wouldn't.
We did consider that question. We just, because in the paper by Roger Meyerson and Jürgen Webel, they also used completely mixed. So we just adopted this.
So is there a reason why we should be interested in this completely mixed focus? That's the motivation for that.
Doesn't this matter for minimality? That if you have a non-complex mixed strategy, you can throw something out already?
That could happen, yeah. That could be one thing that could happen. So if we, for instance, took a pure one and then added a conditionally dominated strategies, the minimality would not work, yeah. So anyway, we took this to be completely mixed, unique and completely mixed, because in Myers and Webel they do the same thing. But that's a good question. I should actually take a note whether we need completely mixed. Okay. Then, of course, there's the question of why is this solution concept preferable to strategically stable sets, right? Because strategic stability, at least in the Mertens formulation by the end of the 80s, that satisfies lots of invariances. And I always get the number wrong. It's something between 9 and 11 or so. So I certainly missed some of those that I listed here. Well, the thing is, this proposition here tells us we do the same thing as strategic stability, essentially. Every solid outcome is supported by a strategy profile in a strategically stable set. So all these invariances are there. And the reason is simply that every component with non-zero index contains a strategically stable set. That is a result that I proved with Stefano also quite some time ago. So all these invariances are there. And moreover, the supporting notion of a game block is something that behaves very nicely. Right? So game blocks, in a sense, are continuous almost everywhere. Or to make the sense precise, here's the proposition about the generic continuity of game blocks. So if we think about the payoff space, so which is the space of payoff assignments to a fixed extensive form, then we can break this apart into a finite number of subsets, where the first one, this U sub naught, is what you could call the critical set. So it's a closed and lower dimensional semi-algebraic subset. And the complement of this critical set is made up of finitely many, is a disjoint union of finitely many sets U1 to UH, such that on each of those components, if you want, the correspondence that assigns game blocks is constant. So in particular, continuous, right? So that's what I mean by generic continuity. On these generic sets, game blocks are actually constant. Okay. So that tells us that the supporting notion behaves very, very nicely over payoff space. And then, oh, I see I'm a bit pressed for time. Then let me turn to what Bernhard already mentioned, sustainability. So the idea, Roger Myerson's idea about sustainability was basically that you look at an equilibrium, a point, and say that this point is sustainable if you can pull away all the other equilibria, and this is the only equilibrium that remains. Okay. Now, Govindan, Laraki, and Paul have a very nice paper where they do this for points, for equilibrium points, and characterize sustainability there. We do that here for blocks. Okay. Otherwise, our concept about sustainable blocks is pretty much a copy of what is done in Govindan and et al., except that we replace the equilibria. So they look at game equilibrium pairs, find an equivalence relation for game equilibrium pairs. We define an equivalence relation for game block pairs, right? So if we have two such pairs, a game and a block for that game, and another pair, a game G prime and a block B prime, we call them block equivalent. If the blocks that are generated by taking the best replies against equilibria in this block or in the phase spanned by the block for both games are actually the same game, identical, except for, you know, relabeling players and strategies. Okay. Then we call such two pairs of game block, a game block pair, we call them block equivalent. Okay. And then for a game G, we call a block B sustainable if it respects equilibrium components, and there is some other game G prime with a block B prime such that the pairs G and B is equivalent to the pair G prime and B prime. But in G prime, the set of all Nash equilibria is contained in the phase spanned by B prime. So that's again this notion of pulling away everything else, all the equilibria that are outside of B, right? So G prime is the game where we've pulled away all the other equilibria that are outside of the phase spanned by the block B. So it's a natural set-valued version of the existing definition of sustainability. And then the proposition says this actually characterizes game blocks. So a block is a game block if and only if it is sustainable. It's the same thing. Okay. So that's our description of our solution concept. And now in the last 5 minutes to satisfy Carl, I'll go through some examples and also show you an application. The first one is not really an application because this is a game that has been developed to test refinement concepts that show in Krebs, the beer cache signaling game. In the beer cache signaling game, we just verify that our solution concept is nice, right? It picks the intuitive equilibrium where player 1 sends the strong signal and player 2 would always fight with at least probability 1/2 if he sees a weak signal, right? That's simply because in this game, there are two equilibrium components, one with index +1 and the other with index 0. Okay. Now here's the application for Carl. It's not from economics, but from political science. And in political science, this is known as the chairman paradox. So this is a committee of 3 people that have to choose an alternative by majority voting. And their preferences, if they would vote sincerely, their preferences are caught in a Condorcet cycle. Okay. this is what is captured by, so lambda is here a number between 0 and 1. So this is captured by these payoffs here. They are caught in the Condorcet cycle. Now this game has two equilibrium components. One that ends up with the most preferred option for the chairman, right? Oh, I should say what the chairman is. The chairman is player 1 here, the guy who chooses matrices. And the chairman has the right to decide which alternative is chosen at a tie. Right? So if the votes tie, then the chairman basically gets his preferred option from the tie. Okay. So one equilibrium component is the one where he actually gets his most preferred option A. The other component is the one where the chairman ends up with his worst or her worst option C, right? That's the one that the chairman really hates, or the chairwoman. Now, this game has a unique solid outcome, and the unique solid outcome is the one where the chairman gets his or her worst option, the option C. Okay? So again, uniqueness. Oops, just 2 minutes left. This here is a game that is well known in literature. It also appears, I think, in my textbook somewhere. This is an outside option game that has two components of equilibrium. One is what the older literature used to call the forward induction equilibrium, where player 1 moves into the subgame, which consists of the first 3 strategies. Right? And the other one is the outside option component. Okay. Now, in this particular game here, the forward induction equilibrium has index -1, and the outside option component has index +2. And the minimal game block here is everything except for the third strategy of player 1. Okay. So in other words, this is a game where both outcomes, both the forward induction outcome and the outside option, are solid outcomes. This is a difference to what Govindan, Laraki, and Pal do, because where they do the point valued sustainability exercise, they take this then actually from points to components of equilibria by offering axioms that end up giving you positive index components. So they would here choose the outside option component, because that has a positive index. And of course, we could do the same thing by just changing the definition of a solid outcome and replacing non-zero by positive, right? But we're a bit hesitant here. So in this game, I think the 3 of us are a bit agnostic on what is the better thing, right? So we declare them both to be solid. And finally, what I already foreshadowed in the introduction, if we look at this coordination game, now it's this coordination game with 3 strategies. This has 7 equilibria, right? The 3 strict ones where the players all coordinate. Then there is 1 completely mixed and 3 partially mixed equilibria between the pairs, the coordination pairs essentially. Right? Now, in this example here, the completely mixed equilibrium, unlike in 2x2 games, right? In this example, the completely mixed equilibrium has index +1. But it does not induce a solid outcome, because there are only 3 minimal game blocks, and those are the strict equilibrium. Right? So our concept here kills the completely mixed equilibrium, because it's not supported in a minimal game block. Again, the Govindan, Laraki, and Pal paper would pick the completely mixed equilibrium as a sustainable equilibrium. Okay, which we don't really like that much, because this is a very unstable equilibrium, which actually in most dynamics that you put here, evolutionary dynamics, it turns into a source. Right? It's not just a saddle, it's a source. Right? It's very unstable. On the other hand, because it has positive index, it's sustainable, the completely mixed equilibrium. And here's actually the game where all the other equilibria are pulled away, if you want, right? And the completely mixed equilibrium is the unique equilibrium. Okay. So this game here that I added 3 strategies over Bernhard's student added 3 strategies. These 3 strategies pull away all the other equilibrium and leaves only the completely mixed one. Right? So there we have to accept the completely mixed equilibrium as the solid outcome. Indeed, the unique minimal game block here is the coordination block of the first 3 strategies. Right? But there is only a unique block that is closed under better replies, and that happens to be the whole strategy space. And this last observation is important to relate this to evolutionary dynamics, because Jürgen and I have a very old paper where we characterize the phases spanned by blocks when they are asymptotically stable, and the characterization is they must be closed under better replies, which is not the case here. So here we accept a solid outcome that in no reasonable evolutionary dynamics can be stable. Okay, and now I'm already 3 minutes over time, so let me summarize. So what we do is we want to combine observability with robustness properties, and that leads us to solid outcomes. And solid outcomes and the supporting concept of game blocks, they have extremely strong robustness and invariance properties, and they can be characterized as being sustainable blocks. An open question is whether we should strengthen this by going from non-zero index to positive index, given the insights that the other sustainability paper has provided. Thanks very much. Any more questions?
Thank you.
That was your kid, right?
So, any questions or remarks, colleagues?
I'm slightly confused by the chairman paradox. You're saying the 0 index, did I remember that well, that the 0 index one is also solid?
No. There's a unique solid outcome here. Only where the chairman gets the worst alternative, his or her worst alternative, that's the unique solid outcome.
And the index 0 is intuitively because she gets to break ties. Is that the reason? That's why she gets the outcome?
Exactly.
Okay.
Yes,
yeah, I see.
Yeah.
So the tie breaking is kind of what shouldn't happen. I mean,
Yes.
That's what you're saying.
Yeah, so the intuition is basically that the other 2 people foresee that in the case of a tie, the chairman would break the tie in his or her favor. Okay. And that's why they actually take the other equilibrium, right? The other outcome. That's the intuition.
Okay. So the paradox prevails.
The paradox prevails, absolutely.
Okay.
Any more questions?
Well, I can always ask a question. Klaus, so as usually very thought-provoking and nice and clear presentation. Thank you very much. What makes a solution concept a good and useful solution concept? So I understand here, very nicely structured things to look at. But as you have this variation, the definition that you haven't made up your mind on, or also this this mixing of these 10-10, how do you want to justify a solution concept? I mean, it's a general question, right? But what is you went through the examples that you liked and tried to support them, or what's the reason why you would support a solution concept?
Because I value existence higher than getting rid of mixed equilibrium. I don't want to.
But then you still have the variation, the definition between positive index and non-zero.
Oh, between positive, yeah. But in this example here, positive index and non-zero index agree because there's only one equilibrium that has index +1.
So it was a general question. How you?
Oh, generally, you mean how?
Right, they're claiming, you are basically claiming that your only way to get things robust is along this path, and the only degrees of freedom you have is in the positive versus non-zero index. That's what you're saying.
Yeah, so indeed, non-zero index does most of the work here for the robustness properties, at least, right? Because non-zero index is, I mean, the idea of the index is to look for robustness, right? That's why it was developed in mathematics. This is not an econ invention. It comes from mathematics and this perturbation theory, essentially, right? So the index gives you robustness properties, right? But that doesn't mean that things are always, or that doesn't make for a compatibility between a rationalistic approach and, say, an evolutionary approach. This is what I wanted to illustrate with the last example, right? So that a rationalistic approach that insists on existence in this game has no choice. You have to pick the only equilibrium there, right? Evolution would say, oh, wait a bit, here things never settle, right? The only block that is closed under better replies, so the only block that can be stable in some evolutionary dynamics from a pretty wide class is the whole strategy space, right? So evolution here would go up and down and back and forth.
But that's good. That's fine. That's fine. We have many games like that. No, that I don't mind. So maybe let me say it differently. It'd be nice to see maybe a property that you would like to have that is equivalent to robustness, and then show that this is equivalent to your solid outcome. Because the way it was presented more, but I don't see the details, is the more you have a concept and you show what properties it has, right?
That is what I meant by robustness. All the propositions basically give you robustness properties. You can take,
but they're not. But they aren't the defining properties. They're not the defining properties. They're you present a sequence of character properties of a given definition instead of starting with desirability and showing that this leads to the definition. But it's probably the same. I'm just thinking about where you come from. That's the thing. But I'll have to think more about it.
In the definition, the definition says the solid outcome has to be induced by the strategies in the component with non-zero index, right? Non-zero index is a formalization of robustness.
But it's the formulation that we want to have. So you're basically saying that this is the one that you want to have. There are a lot of open questions here. In
a sense, yes, that's what I want to have, because that basically boils down to saying that the intersection of the graphs of the best reply correspondence is transverse. And that's what you want, right? And that's the notion that also has been used in many other applications of this branch of mathematics. Okay? Good. All right.
I would have one more question, if I may.
Go ahead.
Yeah, which is the relation.
Hi, Martin, by the way, turn on your camera.
Yeah, I think I did. Oh,
no, I can only see white.
Oh, this is because there's still, okay, now I'm there. Hi. Can you again clarify, because it was very quick, the relation to strategic stability? So there are stable components which are not solid outcomes, right? Or which do not lead to solid outcomes. Is that true? Because you said every solid outcome contains a strategically stable set.
So every solid outcome is supported by a strategy in a strategically stable set.
By a strategy. So, but they, yes. Okay, in a component of a strategically stable set, is that true that they all lead to the same outcome? I guess, right.
So generically, in extensive form space, indeed, all equilibria in the same component lead to the same outcome. Otherwise, this would be a contradiction to the Krebs and Wilson result, right?
Okay.
Because the components are connected, and I could vary continuously. I get a continuum of outcomes. Okay.
Mm-hmm.
So generically, indeed, the outcome is the same for all equilibria in the component. That's why I said earlier, you can support an outcome in different ways of equilibrium.
Yes, sure.
That's how the different strategies come up.
That's clear. Yeah. And now basically, I mean, if I want to have a very coarse picture of your paper, is it fair to say basically you eliminate some of the strategic components, some of the stable sets that you don't like, so to speak.
Yes.
And the others you keep.
Yes, indeed. That's a fair way of saying it, right? that we like strategic stability, but
Yeah.
it has some aspects that we don't like. Right?
Yeah. Yeah.
And those aspects we try to kill. Yes, that's a fair picture. Yeah.
Okay. And basically, if I take now a particular solid outcome and a strategic stable set that supports it, these minimal game blocks that basically
That kill.
induce this.
Yeah.
I don't know how to say this actually. Is there something in these blocks that does not take a positive probability in the supporting strategically stable set?
Can you say that again? I'm not
Yeah,
sure.
you have these game blocks, right? And you say, okay, I need a minimal block for
Yeah.
my concept, right? Now take such a minimal block, take the outcome that you get from there, right?
Yeah.
That's, if I understood right, a unique equilibrium in this, or the outcome of a unique equilibrium of that game, right? That's, if I understood right. Now take the strategically stable set or strategy in the strategic stable that supports this. Now look at the strategic stable set and look at all pure actions that get positive probability under one of these strategies in the strategically stable set. Are they in your game block, or
yes, they must be in the game. Yes, yes.
They are all.
Otherwise, the game block wouldn't respect equilibrium components. Yes.
Okay, and now on the other hand, do you have more, or is the game block coinciding?
We could have more. Yes.
You could have more, and you have examples for that.
Yes, I think so in the old working paper version. Yeah.
Yes, no, it would be interesting to understand what, why do you need these additional poor strategies? What's maybe that helps to understand even deeper the difference between the two things. Okay, it's just an open question that I posed. So
yeah, but it's a good question, and maybe we should take one of those examples from the working paper version into the final version.
Yes, so that one can try to understand. Yeah, and then the only example that I found a little bit on the intuitive level a little bit unreasonable is the one where the one with the forward induction. Does it that so this is the only thing that I which is
the outside option game,
that it selects also the outside option. And you have any deeper understanding why this happens?
Oh, why this happens? So the reason in our framework is pretty simple. The outside, the forward induction equilibrium has index -1, and the outside option component has index +2. So there is not a single component that has index +1. In which case we pick both because we want the index sum to be +1, right? Now, as I said in the presentation, you could go further here, right? You could say based on sustainability, we pick positive index components. Then you would pick the outside option component. Okay, that's actually what Govindan, Laraki, and Pal do, right? So in their approach, only the outside option component is sustainable. We are sort of a bit undecided here at that point in time, at least. But, we haven't discussed this enough. But at the moment, we are more liberal, right?
Can I ask something here? How can an index 2 be sustainable? I mean, when you must change the game because the index cannot be 2 afterwards, and it's a local property.
It's sustainable according. So I should be more precise what they do in their paper. So they have first a characterization of sustainability for regular equilibria.
Okay.
And then they extend this to all games, not only regular games, by axioms, by 2 axioms essentially, and then show that this axiomatization leads to positive index. Okay. So if I buy this extension based on their axioms, then I would have to pick the outside option component with index +2, right? And that would be the sustainable outcome.
So those timeable does not mean unique in a larger game anymore.
No, it does so for regular games.
Okay,
but
not
for non-regular games, it's by these axioms that they pose.
Okay.
Okay. Then let me continue. Just in this forward induction example, I really like the forward induction outcome, not the outside option, right? And if I want to select that, I would have to go for absolute value of the index being equal to 1 or something. I don't know.
What? Come on.
No, but the forward induction
based on orientation, so sign tells you something.
But how should I? I mean, if I want the forward induction outcome, you don't have any support for that.
Sorry?
If I want to select the forward induction outcome, you don't have any supporting.
No, solid outcomes will not support you in that respect. You have to pick some other concept.
Yeah. Okay.
If you want to pick that, but I mean, think of it. It's not so clear, right? I mean, all these forward induction stories, they are based on speeches that players give to each other off equilibrium, knowing that they will never do that because it's off equilibrium, which is strange, right? It's an old debate, actually. This for a long time, I actually didn't understand what forward induction means. It was only until Eric came up with a definition that only applies to two-player games. There it made sense to me. That was the example that I gave was actually a two-player game, right? So it was one of the cases where forward induction makes sense to me. But whether it's generally a reasonable concept, I'm still not sure. I don't know.
But it has an indirect, it is an appeal of assumptions about the reasoning process of players, right? So I see you not taking the outside option. You could have gotten 2. Now there's only one action of yours that could ever give you 3. It's an equilibrium of the continuation game. So, I have to think if Klaus is rational, he must have chosen 3. That the one that
I know all these stories. Yes.
So, and if you think that I'm clever enough to figure this out, okay, you will go for the 3. So I could profit from, a bit of Donald Trumpian story. I could profit from you thinking that I'm stupid. If I also get 3 in the out, let's right. So, but if you think that I'm clever, you will do it.
Yeah, it all depends on how the equilibria are supported, right? And that's all. I mean,
I find this a very reasonable story. I mean, it has all this equilibrium philosophy behind. Okay, all this philosophy that supports, Nash and rationality and so on. If you take it one step further, you do get stuff like forward induction. At least, I think as long as it's consistent with backward induction, say.
I'm probably not such a rational person that I can take it that far.
No, but okay, let's leave it at this. But
I think this is really getting philosophical, right?
Yeah. Okay, but thanks a lot for all your clarification.
Any more
questions?
Just one question. I'm a bit concerned. I'm a bit concerned because you can only restrict yourself to generic extensive form games. And if I see it correctly, if you have something like Cheap Talk or a similar structure, you would be in a subset of, you would be in a non-generic class of games. And I wonder whether there are ways to extend your approach to such games in some form by being perhaps a bit more abstract than just having certain requirements on the best response correspondence or something like that.
So clearly, I mean, that's pretty obvious. There's a very easy way to extend this to all games by just saying it doesn't have to be a unique outcome, but by picking a set of outcomes. So that's completely trivial and easy to do, right? Now, the generic extensive form game really comes, on the one hand, it comes, of course, from the Krebs and Wilson result. On the other hand, it comes from my experience by doing applications. I've never studied in an application a degenerate extensive form game. They're always generic, right? They're never ties, because when you write the thing down, you always have a pretty good idea of how the ties need to be broken. Because you have a situation in mind, what happens, how these players interact. When intermediaries set these prices on high frequency markets, right? They are never indifferent, really, right? I mean,
We don't know
the ties just don't show up when you model these.
So anything like Cheap Talk is not a good game in your sense. Okay.
No. I mean, Cheap Talk is a class of games where you can have these things, right? But again, you assume basically that all the messages cost the same, right? Which will never be the case in reality, right?
Yeah, but you don't know the costs, and that's when
exactly. And then you apply Laplace principle, which is something I've never understood.
Okay.
It has to be the same, just because we don't know. I've never understood that.
Okay. I'll think about it. But yeah, I still think that I don't think that generic extensive form is the only class of games to be considered. There are subclasses which are of interest in themselves.
Sure, and that's why I said there's an obvious way to generalize this to all games, and then you're done. Right? But we wanted to insist on this generic class because I argue basically that's what you need in practice. Right?
Okay.
Please feel free to ask.
Got it. I can't. You're hard to hear.
Sorry, I'm saying if there are further questions, then please people feel free to ask.
Yeah.
And if not, then we thank you. Thank you. I'm stopping the recording now.
Okay. Thanks.